Greetings of the day, dear students. In this video, we are going to discuss about the torque equation of a DC motor, and we will see its derivation, and we will discuss two examples on this topic. This is the derivation we are going to see. Armature torque equals to 0.159 ZP by A into 5 IA, and also we will discuss about the shaft torque and lost torque, and we will discuss one or two examples on this topic, right? If you observe, dear students, please observe, with respect to the motor, the torque developed at the armature is important. In order to calculate the power output, which we can give by power output equals to omega t. Now the torque is measured by what? It is measured by the product of force and the radius at right angle at which the force acts, right? So it is nothing but torque equals to force into perpendicular distance. Here in this context, it is the radius. Now the sum of all the torques due to all the armature conductors is known as gross torque or armature torque. It is denoted with letter TA. I repeat again, the torque due to all armature conductors is known as gross or armature torque. Now let me consider for a given DC machine, here in this context it is the DC motor, where it is going to have the armature, conductors, and number of parallel paths and radius of the armature. Considering all those factors, let me see how to derive the torque equation, right? Let L be the effective length of each conductor, the conductor that is placed in the armature, in meter, and R the average radius of armature in meter, and Z total number of armature conductors, A number of parallel paths. These are the variables we are going to use in this derivation, right? Now I is the total current, I is the current in each conductor, but what about IA? IA is the armature current. Therefore total armature current developed by the armature. Now to know the current in each conductor, already we know the number of parallel paths are A. Therefore I, the current in each conductor, is given by IA divided by A. B be the average flux density in Weber per meter square. 5 flux per pole in Weber. P number of poles. Now from our previous basics, the force on each conductor is given by BIL. Very important, dear students. The force on each conductor is given by F equal to BIL. B indicates average flux density, I indicates current in each conductor, and L indicates length of the conductor. Now the torque due to one conductor is given by torque equals to force into perpendicular distance. Here it is the radius, right? Now the total torque due to Z number of conductors, are there in the armature, right, is given by Z into F into R. But what about F? BIL. So if we substitute F equals to BIL in this equation, we will get Z into BIL into R. But what about I? The current in each conductor is equals to IA, armature current, divided by number of parallel paths, denoted with letter capital A, right? Now B equals to flux per unit area. Let me substitute in the place of I and B these two variables, IA divided by A and B equals to flux per unit area. But what about area? Cross sectional area of the flux per pole of radius R, it is given by 2 pi RL, 2 pi RL whole divided by per pole, it is to be divided by P. Therefore area of cross section of flux per pole of radius R is given by A equals to 2 pi RL by P. Now observe, this is the base equation, Z into F into R. In F we are substituted BIL, and in the place of B we are substituting 5 by A, right? In the place of A, cross sectional area 2 pi RL by P. So after doing the substitutions, observe here 5 by A, IA by A, L into R. Again in the place of A, let me substitute 2 pi RL by P. Now this L and L will get cancelled, R will get cancelled out. Finally we will get TA, armature torque, is equals to, very important, 5 ZPIA by 2 pi A. Z number of conductors, P number of poles, IA armature current, A number of parallel paths. Therefore if you observe, of course this Z P, A are constant. For a given machine, they will be constant. Therefore, if you calculate 1 divided by 2 pi, if you substitute that value 0.159 Zp phi Ia by A. So if you consider this part Zp by A as a constant for a given machine, armature torque is directly proportional to the flux into armature current. Phi Ia, phi Ia, very important. Phi Ia. Dear students, one more important point is, if the machine is shunt motor, what happens is, for example, if it is something like this shunt motor, line current enters like this. Some part of current will flow to the shunt field winding ISH, and this is the shunt field winding RSH, and this is the motor, right? And some part will flow to the armature current, and this is the applied, because of this applied terminal voltage. Because of this applied terminal voltage, current will be drawn by this motor. Now this is armature current, and some back EMF will be generated here, EB, right? So in shunt motor, the flux will be constant. Flux will be constant. But whereas in series motor, the amount of flux in the winding will be directly proportional to the armature current. Therefore, in shunt motor, torque is directly proportional to the armature current. But whereas in series motor, torque is directly proportional to the Ia square, armature current square, Ia square. Clear? So these are the important points. And one more thing. So far, all this torque discussed is which torque? Torque developed at the armature. Torque developed at the armature are also known as gross torque. But the entire torque will not be available to do the useful work. Some amount of torque will be lost because of the friction. And in order to supply some losses, some amount of torque will be lost. Then there will be only some part will be available to do the useful work. That torque is known as shaft torque. The torque which is available to do the useful work is known as shaft torque. Now, how much will be its value? Shaft torque will be how much? It is simply, we know, if it is electrical power we can use the formula VI. If mechanical power output is given by omega into T, right? Omega equals to 2 pi n. N is the revolutions per minute. Now, if you want shaft torque, output power divided by 2 pi n. Output power divided by 2 pi n. Therefore, output divided by 2 pi n by 60. Right? If you further simplify that, 9.55 into output by n. Output by speed n. In n in RPS. In this formula, n should be in RPS. Don't substitute the value of RPM. If you have taken 9.55 into output by n. Clear? Now, the difference between this armature torque and shaft torque is called as lost torque. The torque that is lost, that is to be called as lost torque. The torque that is lost, right? So this is all about the of course, you know, if you have already watched the back EMF developed in the in the DC motor, EB is given by 5ZNP by 60A, where phi is the flux, Z number of conductors, N speed in RPM, P number of poles, A number of parallel paths. A equal to, the number of parallel paths will be 2 if it is wave winding, and A will be equal to P number of poles if it is lap winding, depending upon the type of the winding, right? The A value will be 2 if it is wave winding, A equal to P if it is lap winding. Clear? Right. Now, dear students, observe, let me summarize in this entire discussion. First basic is torque equals to force into perpendicular distance. Torque equals to force into perpendicular distance. Now, the force is BIL, and in the place of B, flux per area, and in the place of I, armature current divided by number of parallel paths, and the area cross section per pole is given by 2 pi RL by P. If you substitute these variables in this torque formula, we will get this equation. Very simple. The key points are, in shunt motor, if it is a shunt motor, flux is constant, so armature torque is directly proportional to the Ia, and if it is series motor, torque is directly proportional to square of the armature current, right? Yeah. Now, dear students, please observe, a DC motor takes 30 amps at 220 volt and runs at 1500 rpm if armature and field resistances are 0.2 ohm and 0.1 ohm respectively. Calculate torque developed in the armature. Very simple. Dear students, the thing required is from the data given, we should be in a position to represent those data with proper variables. The names of the variables are fixed, right? You know, terminal voltage denoted with letter B, but you should not denote this with letter EB, then the entire problem goes wrong. Terminal voltage V, speed M, armature resistance RA, field resistance here specified, field resistance, right? RSC 0.1, armature torque is how much? That is what he is asking, right? So here observe the field resistance is series. A DC series motor, right? The field resistance is in series. Now, what about the power output? Omega into T, right? What about power formula for motor? That is the EB into IA, that is developed at the armature. EB into IA, that is developed at armature. EB into IA equals to omega means 2 pi n by 60 into TA, right? Now, TA, armature torque, equals to EB into IA divided by 2 pi n by 60. It is nothing but 9.55 into EB IA by N. Now, but we don't know EB value, back EMF. If you observe in series motor, field winding will be there like this, and here whatever voltage you have applied at the terminals, okay, will not be, some amount will be lost, where because of this series field winding, because of the current flow in the winding, some amount of voltage is dropped, and because also of the armature also some amount of voltage will be dropped because the current is flowing. Now this current flowing is IA, right? Because of this current flow there is a drop. That drop is how much? Due to armature resistance RA and due to series field resistance RSC. So total IA bracket of RA plus RSC amount of voltage will be wasted or dropped. Remaining thing will be EB. EB equals to V minus IA bracket of RA plus RSC. But in series motor, all are in series. Armature current is same as series field winding current is same as the current that is drawn by the motor. But in the data given, the current drawn by the motor is 30 amps. So indirectly, IA is how much? 30. RA is given 0.2 ohms, RSC 0.1 ohm. Therefore, back EMF EB is how much? 211 volts. EB is 211 volt. Clear? Now, TA 9.55 into EB into IA divided by N. It is around 40.301 Newton meter. That much amount of torque is developed at the armature. 40.301 Newton meter. Clear? Right. Now let me see one more example. A DC motor has 6 poles and flux per pole is 0.05 Weber with lap wound armature of conductors 600. Now the motor speed is 1500 rpm. Determine applied voltage, back EMF if armature resistance is 0.25 ohm and armature current IA is 40 amps, and also determine torque developed by motor. Torque developed by motor. Clear? Observe here from the data given, number of poles are how many? Again, the important point is from the data given, we should be in a position to write the proper variable names. Number of poles P equal to 6, flux per pole 0.05 Weber, lap winding here specified, the winding type is lap. So number of parallel paths A equal to P. P here already given 6 poles. Armature conductors Z denoted with letter, that point should strike to your mind. Of course you know this is 600, you know armature conductors, but the proper variable name through throughout this unit we are following Z. Armature conductors are denoted with letter capital Z. Z equal to 600. Speed in RPM 500. Armature resistance RA 0.25 ohm. Armature current he has specified 40 amps is drawn by the current. IA 40 amps. Now he is asking what is the applied voltage. V equal to how much? Back EMF is how much? Torque developed is how much? Clear? So far clear? Okay. Now we know the formula for back EMF. EB equals to 5ZNP by 60A. 0.05 into 600 into 500 into 6 divided by 60 into 6, we will get 250 volt. But what about terminal voltage? EB equal to V equals to EB plus IA RA. Armature current is known 40. Armature resistance 0.25 ohm. Therefore, it is simply 260 volt. Now, what about torque? EB into IA divided by 2 pi n by 60. 2 pi n by 60. It is simply 9.55 into EB IA by n. 9.55 into EB back EMF we have calculated just now. 250 into armature current 40 divided by speed in RPM 500, we will get 191 Newton meter. Very good. So dear students, please observe in this entire discussion this back EMF EB equals to 5ZNP by 60A. This should be very clear. And V equals to EB plus IA RA, and torque equals to EB IA by 2 pi n by 60. Right? If you know these formulas, it is very easy for us to do this problem. I repeat again, dear students, on seeing the problems, please don't skip the problems in exam. Don't think that for final answer itself you will get the full marks. Please read the problem statement, write the data given, and use the proper formulas, do some such substitutions. For that itself you will be awarded some marks. For final answer, might be some 1 or 2 marks will be allotted. It does not mean that if you get exactly this 191, if this problem is given for 8 marks, it does not mean that if you get exactly 191 then only you will get 8 marks. No. So if the problems are given, please don't be afraid, and please attempt the problems so that you can score the more marks. And the presentation is important. Neatly present the things whatever you know. Show the substitutions, use the formulas. Easily can get good marks. Presentation skills, please improve. Right? Yeah. So this is all about the torque equation of DC motor. Right? Thank you.